Okay, so welcome everyone to IAP at MIT. I hope we have lots of participants from around the world. It's an honor to introduce Stephen Wolfram, who is the creator of Mathematica, Wolfram Alpha, and the Wolfram language. He's the author of A New Kind of Science, the originator of the Wolfram Physics Project, the founder and the CEO of Wolfram Research. Over the course of more than 4 decades, he's been a pioneer in the development, application of computational thinking, and has been responsible for many discoveries, inventions, innovations in science, technology, and business. Pertinent to the webinar today, I'd like to mention 2 things. One is Stephen has been giving Twitch broadcasts for K through 12 students, and I think it was a response to students not being able to go to classes directly during the pandemic. It's a remarkable thing to watch. Just last week, over the course of 40 minutes, he talked about the composition of comets, astrodynamics, brain and cognitive science, and particle physics, all to K through 12 kids. And I think that's a kind of a wonderful contribution. More pertinent to what we're going to talk about today, he's been doing live development sessions on Twitch. It's remarkable to me that they're doing a physics project, but while they're doing it, they're using the language of code and to discuss and develop the physics. And they're using real-time graphics to communicate these ideas. And this, I think, is a paradigm for computational thinking. And so it's an honor to have Stephen begin his talk now.
Great, thanks. All right, well, I'm going to talk about the idea of computation, which and some of its implications. I mean, I kind of think that the idea of computation is sort of the main superpower that's driving forward 21st century science and technology. And in a sense, we are just at the beginning. We haven't really seen anything yet. You know, the engines are just getting started. And I want to talk a little bit about where we've got so far and where we can imagine going in the future. I want to talk both about what one might call computer-assisted thinking and about using computation as an actual paradigm for thinking about things. So I've spent a large part of my life building up the science and technology to do that. It's been a lot of fun making it available for everybody else to use. I think it's a slightly bittersweet thing to realize that one has created lots of artifacts from the future that for many people are still, 50 to 100 years out. I have to say that people like Craig Carter at MIT are people who are managing to drag the future to the present day in very impressive ways. More people can do that. And I want to explain a little bit about that. So I'll show you a bunch of technology. I believe everything I'll show you is freely accessible at MIT. Actually, maybe to begin with, I can show you a little bit of historical context here. Something that I just found yesterday. Let's see. Here we go. Here we go. All right. This is a little artifact from the past. I'm quite an archive keeping person. So this is a printout from July 20th, 1980. This is what the internet used to look like. You connected to @open236, and 236 was a computer at MIT. And so this was actually probably one of the last times I used this machine. I started using it around 1976. This was, so it logs in and it says, welcome to ITS. And then it tells me the mail that I have, which amusingly was at that time about the testing of Bell's inequality in quantum mechanics. In any case, this was, so part of what I want to do today is talk about the trajectory, what happened since 1980. That was the time at which I was just starting to really understand this kind of idea of computational language and just beginning to understand sort of the full power of computation. I'd used it for a number of years as my kind of secret weapon in doing physics. But around 1980 was when I started really understanding its more general application. Well, okay. So what can we do with computation? Well, let me just show you a few things. I mean, I'm sure most of you have seen, I hope, used Wolfram Alpha. if not directly on the web, it's the thing that powers computational knowledge and things like Siri and Alexa and so on. But it kind of gives you a sense of what becomes computational now. So if I say, you know, I can just say something like, you know, something like, you know, do your standard math computation here, and we could probably get an answer. We could even get the machine to tell us a step-by-step solution, which of course is a complete fake relative to how the computer itself did it. This is a constructed for the humans to understand solution, not the way that the computer actually did it itself. We could ask it, I don't know, something like, you know, MIT. Let's see what happens if I type in something like MIT versus Stanford. I don't know what this is going to do as such, but why is it so slow today? I think I'm probably okay. All right, so this is telling us a few facts about MIT and Stanford. And what's sort of interesting about a lot of these kinds of things is what becomes computable. Okay, those are relative Wikipedia page hits. This is information about degrees. We can probably get more data about this if we want to. Let's see what happens if I go there. It might just tell me what that is in terms of academic degree units. Oh no, okay. It's telling me about degrees, but ignoring the word academic there. Well, in any case, we could typing in something like, let's try typing something like this in. Maybe it will interpret that as a genome sequence, and maybe it'll compute where that genome sequence occurs on the human genome. We could maybe dig in and look at what it knows about one of those genes and so on. Do all kinds of things. Oh, I didn't know about that gene. Oh, and you didn't know about it as a yeast gene. That was its default for that particular gene. In any case, we can, the concept here is to be able to provide sort of computational knowledge about all sorts of different kinds of things in the world. I must say, I have to, so in order to make this work, we have to be dealing with understanding the natural language that people type in or say, being able to convert that into something that allows us to actually compute answers to things. I must say, I could tell you a kind of an MIT related story about this. When we were first building Wolfram Alpha, that's now, well, more than 10 years ago now, I had a version of Wolfram Alpha that was working. It was about a couple of weeks before we were going to release it. And I ran into Marvin Minsky, who I'd known for many years, who was a kind of AI pioneer at MIT. And so I said, you know, Marvin, there's this cool thing we've built, and you know, you might find it interesting. And it's like, what is it? Well, you know, it's a question answering system. It's a system that uses computational knowledge to answer questions. And so, you know, type in something and Marvin kind of ignores it and starts talking about something else. And I was like, no, Marvin, you should actually look at this. This time it actually works, because people have been trying to use kind of generic AI methods, trying to use kind of sort of understand everything, kind of imitate the brain type methods to answer questions for many, many decades. Anyway, so then Marvin starts typing in a bunch of queries. I think we even have, because we have logs of these things. We actually have all the queries that Marvin typed. He got so excited about the fact that, oh my God, it actually works. So one question is, how did we manage to make this thing work? Well, the answer is that we were kind of solving a different problem from the traditional kind of make a brain like AI problem. We were solving the problem of converting kind of the natural language questions people ask into something, into a computational language. And this is the result of sort of a lot of what we built is kind of this computational language for representing things about the world. So I'll show you a bit about that. You know, many of you, I'm sure, have seen used Mathematica, Wolfram language, etc. Let's start off and do some things with it. Let's say we want to generate a graph with, let's say, I don't know, 200 nodes, 400 edges. That would be a random graph. We could pick up that graph. We could just do computations with it. So we might say, work out, you know, a community graph plot of that. Oh my gosh, that is remarkable. That is very, very odd. You know, something is, well, let me find out what's happening here. That's a very bad start. this is the, I'm now deeply confused because this is something that is deep in the low-level nervous system of what we do. What is odd? What's odd is that we just generate a bunch of error messages rather than generating a result. I mean, we did generate a result, but we also generated a bunch of error messages, which I find extremely surprising. Well, okay, let's try something else. See whether this is completely broken. Let's try something like a picture of an owl. So we're using natural language here. This is really broken. Something is very wrong here. Oh dear. You know, just before I started this talk, this computer basically showed signs of being deeply sick. I wonder if I should just use another computer. Let me try one other thing. And if that doesn't work, I'm going to use another computer. This computer showed signs of not being properly connected to the network, although it must be connected somewhat to the network because it's talking to you guys on Zoom. All right, let's see whether that looks like it is. Okay, let me see whether this works here. Try this. If this doesn't work, then we are going to have to go to some kind of plan B. All right, let's try our random graph again. I have a bad feeling about this. I have not seen, just before I started here, I just tried to save a file on this computer and it refused to do it. Let's see if this does the same thing. That worked. Well, okay, maybe we're just, maybe something is wrong with that installation. Okay, well, we'll see whether this works. I'm not entirely hopeful here. All right, let's see whether we can save this. That's not the right place at all. Usually I would say that I'm using the very latest pre-release version of things, but this is actually supposedly, unless the wrong thing has been installed on this computer, it's actually the recently released version of the latest version of our language, version 12.2. Okay, so let's try picture of, oh, I'll make it a bit bigger. There we go. Let's say, oops, that was just, I thought I meant picture of a picture. Okay, so let's say picture of a toad. Okay, that looks a bit more promising. Okay, there's an image. It's a bit of a hard to see image. Let's say we want to, for example, let's edge detect that image. Okay, wasn't too exciting. Let's see whether we can actually identify that image. Let's see whether we can, if I ask to use machine learning to identify that image, let's see whether it can succeed in doing that. It has to load in the neural net that it's going to use. And let's see, it's a very dark toad. So an Atlantic Ridley sea turtle. Well, close. I could probably ask it what different things it thought that might be. Let's say the top 10 things, the top 10 possible things that might be, we could ask it. Okay, a variety of different possibilities. We could also ask it, if we wanted to, we could actually see the neural net that it's using to do that computation. Let's see if we can find this image identification network. There we go. So this would be, if I ran this on this, it would show me that, let's just look at that network. So this is showing me the underlying neural net. We can kind of open up this neural net and take a look at what's actually going on inside here. And if we wanted to, we could, for example, we could just do a piece of the computation. We could just take the first, let's say, 5 layers of that neural net, take that image, apply this to that image, get the result. That's not too exciting. Let's see if I say make an image of each of those. Okay, that's kind of the internal thoughts of the neural net as it tried to identify that toad. And for example, if we said, let's do this. Let's say feature space plot. So that will take those images and try and sort of figure out where in feature space they lie. So I guess it just decided the white ones are over there, the black ones are over here. But the important thing that I'm kind of trying to show is the idea is just you want to do a computation, make it easy to set up that computation and do it. And that it's something where we're not just dealing with things that we compute in that are sort of abstract computations. We're also dealing with knowing about the world. So for example, if I said something like, well, let's just get a list of words, for example, this will be by default a list of words in English. Let's say that I want to build up something where I ask a question like take the first letter from each word there, and then let's do that, see what the result is. Okay, now let's make a word cloud showing the first letter of each word of dictionary words in English. And maybe what we can do here, let's try just doing this. Let's try saying, I want to try some other languages as well. So let's just try, that for English, Spanish, Russian, for example. And so now what we're doing is we're just saying, do that operation on those different languages. It might take it a moment to read in those dictionaries. There we go. So now there's sort of the comparative word clouds of those different languages. Or for example, if we wanted to say, we could start doing a little bit of linguistic understanding here. We could say, let's get the translation of the word fish into all languages that we know about. Needless to say, there's some sort of computational things you have to think about. Like here, for example, some languages have multiple words for fish. Many languages have different scripts and so on. We could, for example, say, let's just find the first word. So we're kind of thinking about how we would do this. Let's say we find the first word for fish in all of these languages. And then let's say oops, that was asking at the first. We need to say what's the first word for fish in each of those languages, and then let's go ahead and transliterate all of those, and then maybe we can take. So now we're going to find out what's the most common first. What's the most? Okay, now let's go ahead and take for those. Let's say take the first letter from each of those, and so we're building up something here where we're doing, and let's make a word cloud there. So now we're going to perhaps answer the question, what are the most common first letters for the word fish in different languages? What did I do wrong here? Yes, okay. I need to tell it that I want to do that. Let's just try running this here. Oh, I see what went wrong. We need to tell it that we're not doing this using the letters as weights for our word cloud. There we go. So interestingly, I didn't know that, the most common first letter for a word for fish in the languages that we know about, probably about 500 languages or something, is M. Well, okay, so let's think about other kinds of things we might know about the world. Let's say we want to find, I don't know, capital cities in South America. Again, it's convenient to use natural language to kind of specify what we want. That's converted into our symbolic language, and then we can treat these things just as things that we can compute about. So we can say, make a plot of where all those cities are, or we could go and we could say something like find shortest tour, and that would tell us would solve a traveling salesman problem between those different cities. We could, for example, then take that sequence of cities and find a trajectory, a path between them. Or we could say, let's try something else. Let's try another kind of geo-computation. Let's say battles in the Third Punic War. How about that? I think we probably have data on that. Let's try that. Okay. Oh, there were only 3. Wow. Okay. Well, all right. We can find out where those were. At least, let's say we go, okay, that seems to be right around Carthage. So let's try taking that particular battle, and let's say we want to find what the elevation of land around that was like. So let's say we say 5 miles around that. Let's try and get the geo elevation data, and let's say we want to make a 3D list plot that shows, hopefully, oops, I want to say there, geo range is that. So this will hopefully make us a, what did I do wrong here? Somebody's asking, where is this information being retrieved? This is what we've collected over the last 40 years. It's basically knowledge about all sorts of things about the world. So let's see, maybe that, oh, maybe we don't know where that is. That's the problem. That one was the one, the dot, we didn't know where it was. So let's try this one here. So, no, well, all right, let's try something simpler. Let's try MIT, for example, as a piece of geo data. What is going on here? Something is very, very wrong. Something is not picking up. Oh, that doesn't help. I've got two. Well, that was very silly. That was user error. So hopefully this will work better. Something is very, very wrong with this computer. Okay, there we go. Well, that was a bit of a, okay, so that's very detailed geo-elevation data around MIT. I suspect that's the ocean there, and MIT will probably be somewhere in the middle. If we wanted to, just for fun, we could probably say, let's do this. Let's get, instead of a geo-elevation data, let's get a geo image of that same thing, and then hopefully we can see what happens if we do this. So it's just interesting to see what kinds of things are computable in the world. So we can get hopefully this picture, assuming my computer is actually interacting with the network properly. Okay, there we go. Now we could take that image and I could go and do the other things I was doing before, like let's say I could edge detect that image. And then I could start picking out where's the water in that image and things like that. I could we can deal with all sorts of different kinds of things about the world. So, for example, if I say, give me a random, let's say, give me 10 random movies. Okay, let's see whether I can. If I take those random movies, I could say, show me images of the movie posters from these movies. Okay, there we go. Maybe we could start looking at, let's take, I'm just curious whether this will, well, we could take one of these movies posters and we could try and OCR the text, and I don't know whether it'll work. I'm not sure if it's high enough resolution. Actually, let me do a different thing. Let me, instead of dealing with visual things, let's say I want to say, let's try doing this. Let's try saying audio capture. And let me, okay. Hello, computer. Let's see if you can hear me. Okay, so now I should have got a piece of audio recorded, and now I can get the spectrogram for that. And if I'm feeling very ambitious, I could say, let's try doing speech recognize. And now I can use, so where was that? Line 36. And now I can try and recognize that, see whether it can tell what I said. Okay, close, fairly close. All right, so I mean, they're just all kinds of things that you can compute about in the world. And kind of our concept with Wolfram language is to provide a language that allows one to express all these kinds of ideas and things in the world computationally, and then be able to do computations with them. Well, so maybe I could show you, things are always advancing with what we're doing, and we just released a new version, and there's some, I could perhaps, let me not, because I've been a bit slow already, let me not, oh, okay, let me show you a few things just for fun that we can do here. So for example, here's a new kind of thing. We could take a biosequence that would represent a piece of DNA. We could say something like biosequence translate, and this would now translate that into peptides, and now we could say make that into a molecule. Let's make that into a molecule. Okay, it might take a little while to load some data about that. And then we could say, hopefully, if this comes back, there we go. So there's the molecule that corresponded to the translation of that DNA. And then maybe we could say something like molecule plot 3D of that. And hopefully it will make a nice 3D molecule. There we go. So there's our 3D molecule made out of this. So that was just one small new thing that we added. Let me show you another thing just for fun. This has to do, oops, that wasn't the right thing. Let's see, copy that. There we go. So this is now partial differential equations. So this is kind of, it's getting from the cloud an image there. Let me just go ahead and get that image so you can see what it is. There we go. So it's an image of some kind of shark cutout. So this is now saying solve this as an eigen PDE, taking a Laplacian PDE term with this region as the region to solve over. And now we could say, for example, we could just take that result, that interpolating function result, and we could say plot that over the image mesh that corresponds to this shark creature here. And let's see if we can make that work. And we should be able to get, there we go, there's the first eigenmode of solving the Laplace equation over that shark image. So it's, I mean, there are all kinds of other things I can show you that are kind of new and fun. Let's see if I can pick up one more, maybe something to do with videos. That's a new thing that we're able to deal with. Or I could show you completely different kinds of things. Let's say we say blockchain block data, and we can let's do this. So this should retrieve the most recent block that was mined on the Bitcoin blockchain. By default, it's the Bitcoin blockchain, and we can go and start doing analysis of this, compute things with it, and so on. Or we can actually do transactions on these blockchains and so on as well. So anyway, this is kind of the goal is have a language that can express the kinds of things that we want to talk about sort of anything in the world. And there are lots of different categories of thing that we've spent lots of time making computable knowledge about them. So for instance, let's say, I don't know, let's say you're doing something biomedical. Oh boy, there was a lot of blocks in that. Okay, let's close that up. Let's say a left hand or something, and we could say something like anatomy plot 3D, and that should give us the geometry of a left hand, and we could then go and pick up various bones there and start solving PDEs for them, all kinds of interesting things like that. Anyway, so that's kind of the idea here, is be able to express sort of things one cares about computationally and be able to compute with them. So kind of our goal is to make it kind of as easy as possible for people to just start using this. And part of the way that that's achieved is by having not only the ability to enter computational language, but also to some extent the ability to enter natural language. So for example, one new thing is you can go into you can use Wolfram Alpha. There's actually a whole system called Wolfram Alpha Notebook Edition, or you can use it from inside a standard Wolfram notebook. You could say something like plot, well, let's say, I don't know, plot sine squared x here. And we can enter that in any form we want. And that will now translate that natural language into computational language and do the plots here. So this is kind of an easy way into using Wolfram language, is to use this notebook edition system to just be able to type things in pure natural language. But that only goes so far. I noticed I wrote a little book about using Wolfram language, which you can find on the web. let's see if I can find it myself. Here we go. One of the things I noticed in writing this book is that at the beginning of the book, when I was giving exercises and so on, the exercises were mostly of the form, you know, take this thing that I'm describing in English and put it into Wolfram language. And it was fairly easy to describe it in English for the things early on in the book. By the time I was getting later in the book and we were building up sort of more capability, it became more and more difficult and more frustrating to describe these things in English, because it's like I immediately knew the Wolfram language, computational language version of what I was trying to say, but writing it in English was more and more difficult. And that kind of justified the idea that computational language is what you need to learn if you want to really be able to express kind of more complex things computationally. Okay, well let me so I've sort of tried to give you some flavor of kind of the kind of Wolfram language story, but let me zoom out a little bit and talk about the sort of bigger intellectual picture, and then I'll talk more about kind of how what we've done kind of relates to the future of what's possible in computational thinking. So, sort of a first thing to think about is if you look at kind of the history of science over the last, I don't know, half millennium or something, the biggest idea was this idea from 300 or so years ago that yes, we can use math to represent things in nature and to make models of how the natural world works. But the question, the thing that I got interested in back right around that time, 1980, that I was using that computer at MIT, was yes, a lot can be achieved by using sort of mathematical ideas to understand the world, but how can we generalize this kind of notion of making formal models of the world? How can we go sort of beyond what mathematics alone allows us to do? And what I realized at that time was if we want to make models of things, we have to have some sort of definite rules by which those things operate. But we had a more general way of thinking about rules for things, and that more general way of thinking about rules for things is programs. And so I got interested in the question of what if, instead of using sort of the specific ideas of mathematics of, you know, derivatives and integrals and all those kinds of things, what if we just use arbitrary programs to represent things happening in the world? And so then the first sort of basic science question is, okay, well, what do typical programs actually do? And I started studying a particular type of program called the cellular automaton that's really simple. And let me explain how those work. The idea is this is the program. It's just a rule that says when you have a row of black and white cells, it just says if the configuration of cells in a particular place is white, white, black, make the center cell be black on the next step, and so on. Well, now we can say, so if you use this rule, if you apply that rule, you apply it a bunch of times, let's just start off from one black cell in the middle, and let's just do the little experiment here. Let's see what happens if we just start off with that rule and run it like this. So we have a very simple rule, we get very simple behavior. Okay, let's try a different rule here. Let's say we try rule 250. The set of cases in the rule changes slightly. Now we get a checkerboard pattern. Okay, so then we can try a different rule. Let's say we try rule 90. Now we'll start getting a slightly more elaborate pattern. If we continue this a while longer, let's say we go 400 steps, we'll get a pattern that, although it's even though it started from this very simple rule, you get this very intricate pattern. Although notice that the pattern you get is still in some sense very regular. It's just a simple nested pattern. So you can now say, well, what about doing a sort of a basic computer experiment? You're looking in the sort of computational universe of possible programs. You just ask the question, well, what do typical such programs do? Well, we can just answer that by doing a simple computer experiment. Let's just say we make we just make a table of programs. Let's say programs that they're all numbered just from the decimal version of the binary number that you get here. You can just say, let's do the first 64 of them. Let's just make pictures of what they all do. Here's the result. So each one of these is, in a sense, a different possible model for for how something might work. Many of them, the behavior is extremely simple. Sometimes we'll see these nested patterns, but then in my all-time favorite discovery, Rule 30 here produces rather different behavior. So let's take a look at what that does in more detail. We could say, let's look at what the rule is. This is the rule. This is what it does in more detail. And this is really a remarkable thing because we have a very simple rule. We started off from a very simple initial condition, and yet the behavior we get is really complicated. And for example, if we look at the center column of this pattern, it is for all practical purposes completely random. We used it as a pseudo-random generator in Wolfram language for about 25 years. So it's sort of a surprising intuitional thing that in this computational universe of possible programs, there is extremely complex behavior that is very easy to find. And in a sense, the thing that got me very excited back in the 1980s is it seemed like this is kind of the secret that nature is using to make a lot of the complexity that it makes, whether you're studying fluid dynamics or biology or lots of other kinds of things. This phenomenon that out in the computational universe, even really simple programs can do really complicated things, that seems to be sort of a core story of how nature works. And there are lots of kinds of conclusions that you can make from the fact that this, from sort of the structure of this kind of computational system. So for example, one of them I'm not going to talk about in great detail, though I'm happy to discuss it if people are interested, is a phenomenon I call computational irreducibility. The question is, how can I predict what's going to happen here? Well, one way to figure out what's going to happen is just to run this rule and see what happens. But the question is, can I do what science is famous for letting you do, sort of jump ahead and predict what's going to happen more efficiently than the system itself can do it? And the answer, it turns out, is no, you can't. This is a system that, well, this particular one we don't know for sure, but it's very likely this is an example of a computationally irreducible system where, in a sense, the only way to find out what happens is just to run it and see. There's no way to kind of jump ahead and see what's going to happen. So, okay, so one of the things we discover from sort of looking at the computational universe is there are amazing things that even extremely simple programs can do. There's a great deal of richness in the computational universe. So one of the things that one learns from that is that it's possible to make models directly computationally, to not go through the idea of mathematics, for example, in making models, to just directly make computational models. And so actually, it's been a remarkable thing because for 300 years, basically, when people wanted to make serious models in science, they always turned to mathematical equations to do that. In the last probably 20 years, there's been a remarkable transition that's happened. And if you look at kind of new models that are made of almost anything, you'll find that they tend to be computational, program-based models, not mathematical models. So we've got this situation where sort of the modeling of everything becomes computational. Another thing to realize is sort of in this computational universe of possible programs, there's just amazingly rich things that can happen. And in a sense, a big story of technology, both emerging technology in the future, is kind of the mining of this computational universe. When we build programs kind of step by step ourselves, we tend to set up programs where we can kind of foresee exactly what they're going to do. And they have, in a sense, fairly simple structure. But what's out there in the computational universe are all these programs that can even be set up in a very simple way, but nevertheless have amazingly rich and complex behavior. And that's something that we get to kind of mine. Just like if we're interested in building physical objects, we have to kind of find that there's this substance that exists in nature that's magnetic, or there's this thing that acts as a liquid crystal, and we figure out, how we're going to use that for technology. So similarly, we have this great opportunity to kind of mine the computational universe for useful technology. Well, one of the things that I should mention is in the world of modeling things with in a computational way, lots of modeling with computation has been done over particularly the last 20 years of making sort of foundational models for things in the natural sciences, the social sciences, other places, purely computationally. One place that had been sort of a holdout was fundamental physics. And I've been interested in that for a long time. And I finally, about a year and a half ago, decided to really try and see whether it was possible to use computational ideas to make a fundamental model for physics. And the amazing thing is, it seems to be working. We actually have a real model that seems to provide what's essentially acting as the kind of the machine code underneath physics. And I'm not going to go through this in great detail. You can, there's endless information about this on our website, and there's even an 800-page book that I recently put out about which you can find on the web also, that has lots of information about this. But basically, just to outline what happens, the key idea is sort of in physics, people had thought of space as just being this kind of mathematical construct that we think of as a manifold, and you can sort of put points at any place in space. One of the key ideas here is to think of space much like we know materials like water and so on are made of molecules, to think of space as made of discrete things, kind of atoms of space. And then to imagine that the only thing we know about these atoms of space is how they're connected to each other. And so we build up this kind of hypergraph that represents the relations between these elements of space. The observation is when we have a sufficiently large hypergraph on the aggregate behavior of that thing, just like the aggregate behavior of those bunch of discrete molecules bouncing around in some water might be a fluid, so the aggregate behavior of this bunch of sort of elements of space is the way that we perceive space. Well, it turns out that sort of the first big result, actually I already knew this in the 1990s, is that when you just deal with having these simple rules, a bit like cellular automaton rules, but they're not actually cellular automaton rules. They're rules that operate on this hypergraph. It's a much more sort of flexible system. When you just have these simple rules, you actually get that the feature of space on a large scale reproduces Einstein's equations, it reproduces features of gravity, and so on. And so you can show, just in the same kind of way that you can show that from discrete molecular dynamics you get continuum fluid behavior, so similarly you can show that from this discrete sort of properties of this discrete space you get the continuum Einstein equations. But actually it goes much further than that, because it turns out that one of the features of sort of updating this hypergraph is there are many possible ways to do it. You say, well, which one should you pick? Well, the answer is pick all of them. And you get this thing we call a multi-way system, which represents many different possible histories for the system, for the universe. And what it turns out to be the case is that picking everything, that creation of that multi-way system gives you exactly quantum mechanics. And this is really a remarkable thing. And I think finally I'm about to be able to say that I finally really understand quantum mechanics. And what happens, just to give you a taste of some of the things that happen, in physical space, we have this hypergraph that represents sort of the extension of space. In this multi-way system, we can take sort of slices through this multi-way system. And instead of getting physical space, we get what we call branchial space, which is essentially a map of quantum entanglements. The points here are essentially quantum states. And this is telling us how close different quantum states are in what we call branchial space. So it turns out in physical space, we can derive Einstein's equations. We can derive things like the deflection of geodesics by the presence of energy momentum in physical space. And so then the question is, what happens when we do the same derivation in branchial space? And what happens, and this is kind of I guess my favorite thing so far in what we've done with these models, is it turns out that the direct analog of the Einstein equations in physical space, when applied to branchial space, is the Feynman path integral for quantum mechanics. So in other words, the general relativity is basically the same theory as quantum mechanics, except general relativity operates in this physical space associated with this hypergraph, and quantum mechanics operates in this branchial space associated with the multi-way system. So you can do all kinds of things with this theory, where it's really, really a wonderful thing, because in a sense, what seems to have happened is this theory is kind of a low-level machine code that kind of tells us how the universe is set up. And a lot of the work that's been done in mathematical physics, whether it's in causal set theory, probably also string theory, a bunch of other areas, turns out to be kind of mathematically the equivalent to various kinds of limits of these models. It's a little bit like, I think, what happened with things like Turing machines in the early history of computation. People had other ideas about how computation might be set up. But once you had this sort of concrete idea of Turing machines, you could then go and see how everything fit together and make lots of conclusions from it. So, for example, one of the things that's happening right now, which I find really interesting, is using our models as not just theoretically we can derive the Einstein equations, but this is actually a way of taking general relativity and having essentially a numerical scheme for computing things like black hole mergers, using essentially a different approach to breaking down the way that one thinks about space-time, but one which we actually have an underlying model for why space-time works that way, rather than just saying, oh, you have the Einstein equations, now you do numerical analysis on them. We're doing the same thing with quantum computing. We actually have a nice compiler that goes from kind of quantum circuits down to multi-way systems, and we can do computations within multi-way systems. Actually, the automated theorem proving methodology that we have in Wolfram language is really useful here, because we can start to sort of using that to prove all kinds of theorems directly in our kind of multi-way system framework. Actually, I just have to mention that one of the things that, again, I'm really excited about is this formalism for physics that's based on these kind of arbitrary rewriting of hypergraphs turns out to be a very interesting sort of fundamental model for lots of kinds of things. Just like cellular automata turned out to be good sort of minimal models of lots of kinds of systems, there's also turning out to be minimal models of lots of kinds of systems that we hadn't understood before. One area is in distributed computing. There's a very close analogy between what happens in distributed computing and the issues of distributed computing and the issues of physics. And you can kind of make this dictionary converting between them. Same is true actually in making a sort of distributed version of blockchain that seems to be emerging from looking at, from understanding distributed computing in this kind of physics-based way and being able to import ideas from physics into distributed computing and so on. Well, in any case, so, and there are, well, another area that's really interesting to me at least is thinking about meta-mathematics. Using in the same kind of way. This multi-way system that here represents the evolution of physical states of the universe can also be thought of as something which represents kind of progressive proving of theorems in sort of meta-mathematical space. And so one of the things we've been looking at is kind of to make a bulk theory of meta-mathematics. And in the history of human mathematics, people have proved about 3 million theorems that they've published in the literature of mathematics. But there's a whole sort of space of all possible theorems. And the question is, what does that space look like? And what general conclusions can one make about sort of the limits of the infinite limit of mathematics from that? All right, I'm going off onto things I shouldn't talk about. Oh, another thing we just figured out yesterday, actually, is that we can use these models to make a sort of new discrete underlying model for elasticity theory. That's another interesting direction. But look, the big picture here is computation, and the idea of computational models is something that's very fundamental and that can be used across lots of different fields. And in fact, it now seems like we can actually say for sure that it's really computation all the way down in our actual universe. But the real point is that in this sort of computational universe of possible programs, there's amazing richness in the kinds of things that can happen. So then the question is, so we have all these different kinds of programs. They do all these different kinds of things. Many of them, we look at them and we say, well, that's interesting, but why do we care? So one of the big questions is, how do we take this sort of ocean of computational capability and connect it to things that we humans are interested in doing or that we humans care about? And so as far as I'm concerned, the sort of philosophical point of the development of computational language is to provide this bridge between this sort of ocean of computational possibility and the actuality of what we humans are currently thinking about and want to think about. It's kind of the computational language is this thing that allows us to take our thoughts, formulate them computationally so that we can make use of the power that exists in the computational universe. And that's kind of the sort of philosophical point, I think, of what we're doing. Now, if we look at kind of the history of things, it's interesting to see a couple of transitions that have happened. I mean, for example, if you go back more than about 400 years, you'll find that people who were doing mathematics didn't really have a language. They didn't have a notation for mathematics. They did their mathematics by just expressing it in words or by saying, you know, you move the beads on the abacus in this or that way. But then about 400 years ago, kind of mathematical notation, things like plus signs and equal signs and things like that. I'm not going to finish in 5 minutes. I'm sorry. The thing that the kind of you know, this kind of well, I could, I suppose. Well, anyway, this kind of notion of okay, let's take mathematics that we have been expressing in words, and let's find a kind of streamlined notation for representing these kinds of mathematical ideas. And that streamlined notation turned out to be pretty important because it was what led to the development of algebra and then later calculus, and it basically was what launched the possibility of mathematical science. And so there was a very good run of about 300 years of mathematical science. Now we have this possibility of building science based on computation. But what we need is a language to express computation in a way that we can build those kind of computational X fields. And in a sense, that's what I've spent the last 40 years trying to build, is a computational language that allows you to express things in the world in computational terms to let you build sort of computational X for all X. And I think the thing that we've done here is it's sort of a different direction from the way that people have thought about using computers. People talk about programming languages. What is a programming language? It's a thing that's sort of a wrapper around the actual raw operations of the computer. It lets you define loops and variables and all these kinds of things. It lets you build up the bureaucracy of large programs. Maybe people have added libraries for some particular purposes and so on. But basically, it's a wrapper around the raw operations of a computer. And it's what I've tried to do with our computational language is do something very different, is to take sort of the things that one wants to think about in the world and put them in sort of precise computational terms that allow one to sort of communicate them to a computer and get a computer to help one explore them. So the thing that that's kind of the objective. And I think I could say in the last few years, I think we finally got to the point where we can say that we really have a full-scale computational language in Wolfram language, and that enables just an amazing collection of things. And it enables, sort of the idea is to give one a way to express oneself computationally. And that's something that is useful for many purposes. It's useful both as a way to get the computer to help you do things. It's also useful as a way to sort of crispen up your own thinking, to say, what do I really mean here? What I mean is, and then you can represent what you mean computationally. And by the way, then once you've represented what you mean computationally, the computer can help you work out the consequences. In the case of mathematical notation, we got to the first step of that. It's like, well, how can we formulate what we mean? Well, we've got this mathematical notation that represents it. Unfortunately, at that point, it's like, well, another human can read that, but you can't directly do something with it, or at least you couldn't until you could type it into Wolfram Alpha or something. But the point here with computational language is once you've formulated your thoughts in computational language, the computer can help you work out their consequences. But it's very important, the idea of formulating your thoughts in computational language. And kind of my goal as a language designer is to try to make things so that it's possible to have a piece of computational language that both the computer understands and we humans understand. And so that when somebody shows me a piece of computational language, yes, I can say, okay, I know what that means. Now I can build on top of that. Just as if I looked at a mathematical formula, I might be able to do the same kind of thing. Now, it's work to write computational language in a way that other people can understand, just like it's work to write mathematical formulas in a way that other people can understand. Sometimes you can make a formula that you use for Scratch work that's a big messy thing, and it's not something you show to other people, but you can show it to other people, and it's a way to communicate what you're doing to other people. So one of the things that that I think that there are many things that this enables. This idea of computational language as a way to crystallize your thinking about things, as a way to communicate things to both humans and computers. So one of the things that this thing that I've been typing into is what we call a notebook. We invented these things in 1987. It's a little bit depressing to me that it took 28 years for people to copy this and get all excited about it. The exact precise thing that we did, although it is not a particularly wonderful copy, but it's very, for me, thinking about the ideas that we have of things like the kind of whole notion of symbolic language. I didn't really talk about the foundations of Wolfram language and kind of how it works, and the fact that it's kind of a symbolic language that operates using transformation rules on expressions and so on. All these kinds of ideas, it makes me a little bit I don't know, nervous or something that it took 28 years for people to even understand this idea of notebooks, which I consider to be a totally trivial idea. These deeper ideas that are what make the Wolfram language possible, I think are still, after 40 years, people don't really quite understand them for the most part. I think the thing that, and I realized with things like our physics project, that is built on top of kind of this stack of ideas about the way computation works, and on top of the ability to actually do computer experiments and so on. And I've sort of realized it's rather satisfying in a way that if we hadn't done it, it probably would have been a very, very long time before people would have gotten around to doing it. But in any case, this idea of notebooks enables, I can turn this into, this is, I could say a computer experiment and so on, and I can start explaining what I'm doing here. And what this enables is the idea of a computational essay. And so I've been kind of pushing this for a few years now. I know Craig Carter has done some wonderful things with these at MIT. The idea is this is a way to express yourself. You express yourself in a mixture of natural language and computational language, and perhaps math. In fact, one thing that's just been added in version 12.2, if you're really a tech user, let's see if I'm still enough of a tech user to be able to do this. Yeah, there we go. You can actually enter your math. If your math is kind of meaningless to Wolfram language, you can always enter it in tech and have it rendered directly in the notebook and so on. So in any case, the thing that, so the idea of a computational essay is to express yourself in a mixture of natural language and computational language. And it's a really powerful thing. It's a powerful way to collect your own thoughts. It's what I produce every single day, are essentially computational essays, notebooks that represent the work that I'm doing on a particular day. I could probably show you the ones I did just last night if you're curious. In fact, in kind of our sort of radical openness mechanism of doing things, we actually post let's see, I could probably find, let's see, 2021. I wonder whether my things from last night are up yet. Not quite from last night. Looks like the most recent. Oh no, there we go. Yeah, there are some things. Yeah, here we go. Yes, this probably is literally from last night. This is my my notebook. This, you can probably open it in the cloud here, maybe. Yeah, there we go. Okay, I was studying non-deterministic Turing machines because they will help us understand. Well, yeah, that wasn't so exciting, but there are some. That's what I was doing last night, and this is just a notebook running in the cloud here. You can run Wolfram language not only on the desktop but also in the cloud, and you could go to this, make your own copy, and start telling me what I should have figured out last night but didn't. But in any case, this idea of computational essays, very powerful way to express yourself, to communicate information, and it has kind of the nice feature that not only do you read it, but you can also run it, and other people can build on it. And so, back in the old days, maybe 100 years ago or so, people in school, like K through 12 school, would do these things, make these things called ciphering books, which were kind of examples of, they would work through over the course of years, a bunch of kind of mathematical calculations and so on. They would keep these books for the rest of their lives as a way to remember how to do these computations. Well, you can do the same kind of thing with computational essays, except now you don't just get to read them, you get to actually run the code. And it's really nice to see how people are able to build up from computational essays. We don't yet have, I've been waiting for this for 35 years, for computational journals that really allow one to use computational essays and really have sort of computational language that works in them and that's readable in them. But we can already see from the things we're doing ourselves, for example, in our physics project, everything we're doing in our physics project is available as computational essays, and people build on it. And for example, right now, we actually have a physics project winter school going on. We limited the enrollment of that to 20 people, so it's about 20 physicists working on things to do with our physics project. And it's really cool to see that they're able to make these amazing graphics and do these amazing computations because they can just pick up the things that came from computational essays that I wrote or other people working on the project wrote and start going from there. I was just yesterday looking at things that some of these students were doing, and a lot of it is beautiful, but a few of these students were infected by probably Python or Java or something like that, and are writing things like, you know, for I equals 1, I less than whatever, I plus plus, do this. That's probably C, I think. That was that infection, and it's kind of depressing to see that, because it's like, okay, you should just be writing something like, you know, something like this to make a table of squares. You should not be writing, you know, you should not be pandering to the very low levels of the computer and saying, you know, okay, computer, you're going to store this data in a register in this place and do this, and, you know, add this piece to that. That's not what computation is about. It's like, you know, if you want to get from place A to place B, you can go study how cars work, but that's not the same thing as being able to drive the car to get to where you want to go. And part of what I've tried to do is to sort of make it so that we have a computational language that lets people make use of the ideas of computation without having to think about the low levels of what's going on. Now, I have to say, it's really kind of neat. You can do things in Wolfram language. Actually, you can take actually, this is a recent thing, is if you really want to deal with low-level data structures, you can actually do them in nice. You know, you can get your linked list, and you probably get even get a visualization of the linked list, and you can do all those linked list operations that you might learn in computer science. Much as I like computer science, I would say that I think the thing to realize is computational X is not something for which the ideas of what's usually in computer science are the most critical things. The most critical things are kind of getting you as quickly as possible to being able to make use of computational ideas in what you're doing. And well, I had a bunch of other things to say about sort of the educational process of computational X, but it's more fun to have a discussion. So let's maybe I should stop here, and we should turn this over to discussion. But I think that the main point I've been trying to make is there's kind of this notion of thinking about things computationally, having a computational language in which to do that thinking computationally, using that computational language as essentially the notation to build computational X for all X. That's kind of the notion here. And just as a practicality, maybe I can, let's do this. Let's say publish to cloud. Let's take this notebook that I've been using, and let's go ahead and publish it. May have some big things in it, I'm not sure. Or we may still be the victims of whatever horror happened to my computer here. But anyway, so this is now publishing that notebook to the cloud. And oh, if we were in person, we could show that barcode and people could pick it up on their phones. But in virtual form, it's much easier for me to put this in the Zoom chat. And let's do that. And people can play with that now if they want to. So that was at least a rough version of what I thought I would say here. So let's happy to have discussion. So please.
Thank you very much, Stephen. I'm sure that you can't hear it, but everybody out there is clapping. And so, thanks for that. Great, we get a chance to have a panel here. The other panelist besides Stephen is going to be Ike Chuang. Ike Chuang is known to all of us at MIT. He is the go-to guy for computational thinking. He's the guy I always talk to. And he has written a fundamental book on quantum computing. And many of you know him as being the chief architect for MIT Access Platform. And he's also the Dean of Digital Education at MIT. And so I consider Ike a friend, and I'm very happy to have him here. So we're going to have a panel. I'm going to start by asking a few questions to the panelists and get some brief answers. But I want to give Ike a chance to ask a question first.
Thanks, Greg. It's a pleasure to be here. Just a correction of fact, I'm not Dean, but Krishna Rajagopal is Dean. I'm Senior Associate Dean for What That Matters. Steve, that was a beautiful talk, visionary as always. And it made me curious to think of civilizations. Civilizations, after figuring out survival, often develop languages. And after a language comes something more like culture and society. And I'm curious, therefore, what will Wolfram civilization look like?
Right. That's an interesting question. I have thought a bit about this. I mean, so what is enabled if people, literacy in human language came in large scale, maybe 500 years ago, and it enabled lots of kinds of structures in the world. What will sort of being able to express oneself computationally, what will that lead to? So sort of among the more controversial things to think about is what is computational democracy? What forms of organization can you have? And there's interesting thought experiments. It's not something I figured out, but it's something that you can imagine. What if everybody, instead of casting their vote for this, that, or the other thing, could write a computational essay that says what they want the world to be like? What if you could feed all of those to this big AI and have it say, well, then this is what you should do? Now, of course, you're thrust right into, the old questions of political philosophy. This makes 5% of the people very happy and 10% of the people very unhappy. What should you do? All those kinds of things. But it's interesting as a thought experiment. And what one can, I think, expect to see is kind of a lot of different structures that can develop. But I think, one of the things that what one realizes in terms of making these predictions is a little bit horrifying to me, at least, is I came up with this idea of computational irreducibility back in the 1980s, and I thought of it as a sort of an interesting scientific thing. And then the world rolls forward a few decades, and then I realized that, oh my gosh, when people are doing blockchains and particularly Bitcoin, there's this thing that's being done, and it's being done to sort of a way to generate an idea of value, and it is basically grinding computational irreducibility. These giant farms that are doing Bitcoin mining and are using up, the total electrical output of the size of Denmark or something, that is computational irreducibility. And actually, I'm pretty sure that the inventor of Bitcoin actually was well aware of my work on computational irreducibility, and that was sort of a seed for those ideas. So it's kind of a strange thing. You have this, what you think of as a scientific idea, and it turns itself into something that gets used in the world in an absolutely bizarre and unexpected way. No, I think that in terms of so yes, I mean, another issue with sort of computational language is, okay, we have AIs and we say we want the AIs to behave in a certain way. We would like the AIs to be like nice to humans. What does that mean? How do we write those laws to say, okay, AIs, be nice to humans? We have to have some kind of computational language in which to express that. Those are the kinds of things we're dealing with. Now, sort of the intuition that you get from thinking about computation is also very important. Like computational irreducibility is a directly relevant thing in thinking about sort of things about the world. For example, I was involved a bit in this whole question about how do you tell if kind of the ways that you pick content, the way that Facebook or Twitter or Google picks content, is that sort of ethically okay, or is that consistent with values of some kind? How do you figure that out? And you might say, well, just look at the code, it'll tell you. But computational irreducibility says you can't do that. I even managed to get the term computational irreducibility into the congressional record about a year and a half ago, talking about this stuff. But in any case, this is a place where the intuitive understanding of that is important. Now, computational language, again, gives you a way to express sort of a set of values that you might then want to impose on, for example, the newsfeed that you get and things like this. But it's an interesting question. I think about it. I don't really know the answers. I never would have guessed Bitcoin mining from computational irreducibility. So that gives me a little bit of humility in terms of one's ability to foresee what's going to happen. But I think, I think in the world of science, for example, it's pretty clear that, a big part of the story is, for every field X, there is going to be a computational X. And not only is the language in which one is doing the field going to be computational, but the ways of thinking about things in that field will be computational, and things like computational reducibility and so on will be things people really realize are important. And they're not just, oh, people had thought about, computers as just the that thing off in the corner that validated things I was otherwise doing, but that's not the right story. The right story is, computation is the sort of front and center idea that's kind of dragging these areas of science with it, I think.
I'm going to bring up a question for both Ike and Stephen. Stephen, in your talk, you were talking about writing the introduction book that you wrote, and you said writing in English became difficult about halfway through the book, and it said coding became an easier way to communicate what you were thinking about. And I think that this is interesting. It certainly is my experience as well. Coding becomes an easier way to communicate things. But I think many of my colleagues in the humanities and social science will misinterpret this as saying writing will become archaic. It will become superseded by coding, or things like dance or theater arts will become superseded by coding. And I just want to get some discussion about whether we as a group really mean that or not. I'm trying to
Oh, I believe very much in writing. I mean, no, look, it's about expressing things clearly. Writing in natural language is a good way to do that, but this is a way to extend that. This is a way to express things we've never been able to express before. There are things we've been able to express perfectly well in natural language, but there's more that we can express. And I think, actually, I think that the notion of sort of exposition, computational language forces a bunch of the kinds of thinking that are important for good exposition on people in a way where the computer, it just doesn't work if you don't express it in a clear way. Whereas in English, you can get away with writing all kinds of nonsense, and it's only up to a person to read it and not understand what you're talking about. With computational language, you have an actual audience. The audience is the computer. And if you can't explain yourself to the computer, you're not doing the right thing. At least that would be my point of view. I might also say that in terms of the adoption of these kinds of ideas, what I've noticed is it's strange. You might think the people in the very STEMmy fields, I see this particularly in K through 12 education. It is often the head of the English department who becomes the great sort of computational thinking person, not the person who's been the long time, I don't know, engineering teacher or math teacher or whatever else. It's a way of thinking about things, and people have often been locked out of that way of thinking about things because they're not into the details of writing, for loops and so on. And this is a way to get those people into this kind of thinking, and they're often very good at this kind of thinking. They're just not very good at those details. I might just say one thing. When I was a kid, I got interested in physics when I was pretty young, and I really didn't like doing all those detailed things in math and chasing minus signs and all that kind of thing. And the thing that got me into making computers do that was precisely, I didn't like doing it, and I probably would have been completely blocked from doing things in physics and so on, because I wasn't a big minus sign chaser. But me with a computer, it was pretty good. Me without a computer, hopeless. But with a computer, I could, I had a sort of superpower and could go further than other people could. Anyway, that's my point of view about that. Any thoughts?
I'm actually very much with Stephen on this. In fact, maybe let me share it as a story. Motivated by many of the same ideas that Stephen has just said, that computational thinking can actually be very empowering to humanities rather than something which takes away. I was one of the co-creators of a class called How to Make Almost Anything, which is basically a shop class meant to teach to artists and young kids how to use the most dangerous of instruments, big machines, CNC plasma cutters, as well as the most complex computers that people can get, but use them to do what you want and express what you want. We taught Arduinos, we taught CNC milling machines, lathes, and what resulted to people who had no background in electronics or programming or machining. And to people who went through this class, it was really, really empowering to be able to use your hands to control the world around you to express your thoughts. For example, one of the most interesting projects that resulted was this artist, I think her name was Kelly, who made a bag you could scream into. So she could scream into it and then capture the scream, run outside and let it replay her scream so that she could release all that built up tension and energy somewhere else, maybe over and over again. And it was her expression of so much about humanity going into a piece of creation that was enabled by computational thinking.
You know, I think one of the things I like to say is that, you know, what we're trying to do is to go as immediately as possible from ideas to reality, so to speak, to be able to go from the things you're thinking about to be able to actualize that. And I see that when people, you know, learn Wolfram language, there's a point at which they are fluently able to start going from, oh, I wonder about this thing in the world. Like I was just wondering this morning, I saw the title of this talk about computational thinking for computational N for all N. So I was curious, what actually are the N's for MIT? I was actually pretty surprised. It's a very interesting piece of history you have there with, you know, civil engineering, mechanical engineering, architecture, et cetera, in the low values of N. But I was thinking to myself, okay, I didn't quite have time to do it, but I was thinking, okay, I did get as far as typing in the one line to import that web page and start seeing whether I could grind it up and make conclusions from it. But the thing that gets interesting is when you can fluently take oh, I wonder about this, and in a matter of a few minutes, actually have that picture up there and be able to say, oh, now I understand this. And, you know, I've seen that with lots of people, including lots of kids and so on, get to the point where they're fluent enough in computational language, in our computational language, to be able to do that. And it's really neat. And, you know, it's something where it's an incredibly valuable skill that can be applied to anything. And it can be applied, you know, you talk about things like, I don't know, dance. You know, I've seen people apply our stuff to all kinds of funky things with capturing motion from dance and then trying to conclude things about it and do machine learning and all these sorts of things. But, you know, the idea, the thing one should be teaching, I think, in computational thinking is, you know, let's say you're dealing with dance. What could you imagine doing computationally? How could computation do something with that? And, you know, do you know enough to be able to do it? Do you know, do you have an idea of what does image processing correspond to? What does, what does it mean to talk about three-dimensional motions here or there? What does it, how can you imagine taking some choreographic representation and turning it into a symbolic form and so on? These are the kinds of things which people should understand, and the mechanics of how you actually do it, that's up to people like me to try and make as automatic as possible. But the thing to really have people learn is, how do you take kind of this, how do you take what you're thinking about and turn it into computational form? And I suspect, I'd like to know from a sort of the way universities work, for example, this is something where there is so much opportunity. I mean, all these fields can be so revolutionized by kind of this paradigm that we have, which is the dominant paradigm of the 21st century. I mean, it is the emerging dominant paradigm. I noticed that at MIT, you've recognized that with a whole College of Computing kind of thing. And, but how do you actually get there? And do you, what is the, how do you, what I've tried to provide is a stack of technology to make it possible for people to get to sort of the computational thinking point without going through kind of the how does the car work inside kind of thing. I've tried to define, and I'm actually going to work on it some more in the next year, sort of what is the optimal path for taking people who don't know anything about computation to being able to do computation. I mean, I might say one thing that I've noticed is the thing that one has to avoid in teaching like coding to kids is having the same thing happen to coding to kids as happened to math for kids. Because basically the number one thing most people say about math is, I don't like math. Now, the fact is, that's because they were exposed to extremely grindy mechanical math in school, which they perhaps weren't very good at and didn't particularly like, as I didn't particularly like. And, that's what happens if you insist on feeding people sort of a thing that is kind of the low-level mechanics rather than the actual payoff, which is being able to make use of those kinds of things. Now in math, we didn't have that opportunity. We didn't have the possibility, or it's much more difficult to say, just jump to the end. just make use of all those cool ideas in math. You don't have to learn how to add fractions or whatever else. We've had a little bit more opportunity to do that with tools that, between calculators and things I've built and things other people have built and so on. But with computation, we really do have that opportunity. And I think that's an important thing to realize is, we've got this opportunity to really teach people sort of computational thinking without teaching the detailed mechanics of computation. Not that the details of mechanics of computation aren't totally fascinating. I mean, I've spent a large part of my life interested in those things, but I don't think it's for everybody. But I'm curious from I've sort of wondered, will computation be taught like math is taught, where there are sort of service classes taught by one group of people? Sometimes they're taught within a particular department. Sometimes they're taught centrally. What's the right way to get people to the point where, a bunch of universities have done things with our technology where they, teach every student sort of basics of Wolfram language so that they can then use it in other classes. But the question is, what's the right path for doing that?
I think that's something that we are struggling with right now, is what is the right way to do it and how to agree about that. I just want to say one thing. You said this idea, this step between wondering about something and doing it, perhaps making a few mistakes along the way, strikes me as one of the most effective ways that I learn something new, in addition to discovering something new. I want to ask a question about a bit more of a historical question. And is computational thinking really something that's new, or is it something that's been around for a while and is becoming current because we're in the middle of, let's say, a Gutenberg printing press moment, and we have this availability of all these machines every place, and computation becomes natural? Or is this something that is kind of fundamental in the way that we've been thinking for a long time? Thoughts?
I can try, and it's actually new. I mean, I've studied this history in great detail. It's actually new. I mean, what happened is, like Leibniz had the idea of kind of making sort of a logic that could explain legal cases and do lots of other kinds of things. In fact, Leibniz is a cautionary tale for people like me, because Leibniz basically imagined Wolfram alpha, but in 1700, and it was a bit too early. You just couldn't get there. He built a mechanical computer out of brass. He kind of campaigned with various dukes to collect information in libraries and things to make it possible to make a Wolfram alpha-like thing. But it was 300 years too early. But I think that he had some of those ideas. They really resurfaced, actually, interestingly, about almost exactly 100 years ago. December 7th, 1920, was a very visionary talk given by a guy called Moses Schoenfinkel, who most people have not heard of, who was the guy who invented these things called combinators. They were, in fact, the first sort of real abstract representation for computation as we now know it. And even today, they're extremely obscure. Even today, people find them hard to understand. I think in Wolfram language, we have all but one of the ideas from Moses Schoenfinkel are deeply embedded in the structure of the language. The one idea is no named variables. That was something that Moses Schoenfinkel had, which us humans, I think, find really, really difficult to understand. But in any case, but the idea is that came through Gödel's theorem and then to Turing machines in 1936 and so on. This notion of computation as a foundation for thinking about the world really is something surprisingly new. I mean, for example, when you look at cellular automata, I've been thinking one day we'll unearth, a Babylonian, tablet that has a cellular automaton on it. But it hasn't happened yet. I mean, it could happen. There's nothing about cellular automata that doesn't make that a conceivable possibility. They're not, difficult to understand at that level. But I think this notion of applying rules and doing so repeatedly, and this idea of programmability and so on, this really is a new idea. I mean, it's something fundamentally new that is also surprisingly something that new since, for example, public K-12 education came into existence. And it's the first really new thing, I think, that's come up in the last 100 and something years that has not, where it wasn't just, oh, it's just like this other thing that happened before. And the thing to me that's been surprising is, as I've worked on this over the years, it's like every time I think I have sort of a new level of understanding, that provides a platform to go even further. That's at least that's, you know, I feel pretty strongly this is actually something new in history. I mean, usually one can say, and I've been much involved in doing this and saying, well, actually, you know, there was a precursor of this long ago. I mean, our physics project, in a sense, you know, the ancient Greek philosophers, their big idea was the universe is made of lots of identical discrete objects. We're, in a sense, doing the modern version of that, but we're doing a modern version of that informed by one important new idea, which is this idea of computation. At least that's. Yeah.
I would take an opposing viewpoint, actually, because these days, let's see, kids would say, okay, programming a computer is just like baking cookies. There's a recipe and you follow the instructions one step after another. So if you identify computational thinking with procedural thinking, 1, 2, 3, 4, and a recipe, then it's extremely old. It's almost as old as knowledge itself for humankind. But there's one sense in which I might agree with you, which is to say that there's an essence of something new in computational thinking that's maybe even still missing from Wolfram language, as if there could be something. And that would be something about crowds, collections, concurrency, time. In computer science, this is the big thing about computational thinking today. Suppose we call it modern computational thinking, just as a way to distinguish this. Distributed computation is the novelty of our day and age today, clouds. Yet I don't have such a sense, like in Wolfram language, of a concept immediately at hand of what happens simultaneously with what, and how do you lock one thing versus another? No semaphores, no notion of massive parallelism at your fingertips. And yet that's what's happening now. And maybe that's what's new about societies of computers, the notion that there are many independent actors all happening simultaneously, and we need a way to computationally think about that process. That's almost much more closely aligned with what humans do, because we have a language, but we also have this simultaneity that's happening. And it's resulted in amazing things like Wikipedia, because you can now crowdsource things computationally. You have CAPTCHAs, you have many, many other things. We have now the number of authors, average authors on a scientific publication has skyrocketed in the last few years because the ability to work together in teams has dramatically exploded. And if there's one thing I might ask from Mathematica, it would be that ability to work in teams on something rather than as individuals on something. And I think computers and computational thinking is going through a revolution that's almost like the Gutenberg press in that one way today.
Okay, let me very interesting points. These are great points. Okay, first thing, recipes and procedural thinking. I do not agree that computational thinking is the same as procedural thinking. I think the procedural thinking that is what gave us kind of this low-level notion of computation. This make the computer do this, then this, then this. Computational thinking is about take that whole, that whole lump of stuff and, apply some image processing operation on it. Take it, think about how do you think about this whole object and do something to it. Now, you might do a series of operations to it, but I don't think that's the important thing. The important thing is, what kind of a thing do you do? I mean, it's more like, what is the individual baking operation? And think about baking, but not baking, but some more, some computational generalization of baking. I think that the sequential aspect of it is actually is not the important thing. I mean, it's great that people understand that. People, see, this is the thing. People sometimes imagine that if you break things down into procedural operations, then it will be easier for people to understand. This is not true. I mean, it's simply, this is the thing we've learned. I didn't know how untrue that was before I started designing computer languages. That, people really get this notion of you can take this whole thing and do something to it. You can take this, and one thing to realize is there are things to understand. It's just like you can walk up to mathematics and you can say, oh, it's all obvious. I don't need to learn calculus. I can just figure it all out for myself. Well, people typically can't. People typically have to actually learn something. And I know for computational language, there are certain things like the notion of higher order functions. That's one that actually is people end up having to learn it. And it takes, some people have a hard time at first learning it. It's like the notion of a function, actually, in calculus. People have a hard time, it's a bit abstract. Once people get it, they're off and running, but there are things to learn. Now, in terms of parallel and distributed computation, you're absolutely right. In Wolfram language as it is now, we have a nice mechanism for doing practical parallel computation. You know, I use it every day. I have a network of about 100 cores, and I use, parallel table all the time, and it works beautifully. And it's very convenient. We just added the capability to run, convenient Amazon batch jobs and so on, where you can just take this piece of Wolfram language code and say run it in this whole external environment. But in terms of the question of sort of understanding how computation works in parallel, that is a super interesting question. And I might have said I have little to say about that question, but for our physics project. With our physics project, I have a lot to say about that question, because actually that multi-way system thing that I was showing, that is the thing that corresponds to quantum mechanics in our models, is precisely doing parallel computation. That's what it's all about. And in fact, if I can show you, let's do something really, I'll show you something from yesterday. Okay, so I told you I was looking at non-deterministic Turing machines. Let me see if I can pull something up here. Let's see where I can find it. This is, let's see, where is it? Well, the basic point is what for example, a race condition in distributed computing, that is a result. That's the analog of what we call a branch pair in physics. It's deeply related to the uncertainty principle in physics. It comes about because of, you can think about it as coming about from a curvature in this branchial space. And what I think is really interesting, and sort of my sort of excitement about that right now, is that the idea in distributed computing, sort of a big notion is, how do you keep in mind all these different things that are all happening sort of at the same time? That's actually pretty hard for humans to do. And what I realized is, if you think about space, the things that are happening in space, everything that's happening in a different place in space could be happening quite incoherently. But we as humans organize space by thinking about, there's this thing that happens at a certain moment in time throughout space. This is a feature of the fact that our brains process information quite slowly compared to the speed of light. So we're used to the idea that there's this whole area of the universe that we can see that is in a certain state at a certain time. So we organize space-time in that way. And in our models, this is, we foliate the causal graph of causal relationships between events in that kind of way. But what one realizes is that in a sense, we are organizing our thinking about space-time using reference frames. That's what's natural to us from our sensory system. Well, turns out one could do the same thing in distributed computing, and one can actually think about programming in a certain reference frame. And so when one has, a key idea here is this thing we call causal invariance, which is the same as eventual consistency in distributed databases, which is the same as the Church-Rosser property in mathematical logic, et cetera, et cetera, et cetera. Slight details and differences, but the basic point is that relativity in physics is the statement that it doesn't matter which inertial reference frame you're picking. There is a similar statement about distributed computing, and it allows you to think about, oh, I'm programming in this reference frame, and that's the one where it's easiest for me to understand what's going on, but it's equivalent to being in some other reference frame. And when you can start thinking about event horizons and the role of event horizons in distributed computing, et cetera, et cetera, et cetera. Anyway, the thing that I've been literally the last week actually been really grappling with is in our models of quantum mechanics, the quantum, so we have this notion that is the analog of reference frames in physical space is these things we call quantum observation frames in branchial space. And one of the things that happens is, oh gosh, how to explain this easily? Well, but basically the reason that relativity works is because we observers are embedded in the same causal network that everything else that's happening in space-time is embedded in. The big mystery in quantum mechanics is, why do people think that definite things happen? Quantum mechanics is talking about all these different probabilities of different things happening, but yet we think that definite things happen. How can that be? And the answer, I think, is that if you think about things in terms of this branching multi-way system thing, when we are embedded in that multi-way system, our brains are in a sense branching in the same way that the rest of the universe is branching. So it's in a sense, how is the branching brain reading the branching of the universe? And this is what you then realize is that I think the essence, and this is again something I've recently figured out, and it's still unfinished, but I had long been claiming, when people ask me, what about consciousness? I'd long been saying, I don't have anything to say about that. And I would tell this whole story about life and intelligence and how, you know, when you generalize those notions, you end up with just sort of generic computation, and consciousness are the same way. But what I realized is, actually, I think consciousness is very much to do with this ability to integrate a stream of stimuli in such a way that you can, you have this definite stream of things that are going on, as opposed to just all these random operations happening incoherently in the world. And I think what happens in parallel computation, and the reason we find it difficult, is that in a sense what's happening to make use of it in the best possible way. I mean, this is a quintessential example of parallel computation. Every cell just does its own thing, and it all happens in parallel. We have a very hard time understanding what's happening unless we have a way to sort of corral it into something that sort of maps into our consciousness and allows us to sort of deal with it as this single sort of thread of existence. And by the way, language, I think, captures well that sort of single thread of existence, that single thread of representing things. And I think, anyway, I was just going to show you one thing, if I can pull it up. Let's see whether I can. I don't know whether I can. This is a, okay, here we go. This is literally from yesterday. So that's a typical, your average communal garden Turing machine. There's the rules for the Turing machine. That's the operation of the Turing machine. Now, that's an ordinary Turing machine. That's a just does one thing, single thread of computation. This is.
We're seeing your whole desktop. I think you want to bring one up, one of your notebooks up.
What? You see. Let's see.
Yeah.
That one? Is that?
Yes, that's probably the one. Yes. Yep.
Okay. All right. Okay. So this is okay, Turing machine. If you weren't seeing this before, this is now it. Maybe I was showing you all kinds of other random irrelevant stuff. Sorry. Okay. So there's a Turing machine, ordinary sequential deterministic Turing machine. There are its rules. Let's say we add a rule that is ambiguous. So it says when it's in that state on that color, it can do two different things. Well, then we get a multi-way system. Instead of just getting the single possible path of evolution, we get many possible paths of evolution. The particular deterministic Turing machine might follow that one path. This whole thing here is a multi-way system that represents all the possible paths that the Turing machine can follow. So the question is, well, we know some of the stuff I did 20 years ago now, we know the simplest universal deterministic Turing machine. Here it is. That's now the question is, if you have a non-deterministic Turing machine, what can you say about how that behaves? And so I was just starting to explore these non-deterministic, these multi-way Turing machines. And the question really is, how do you think about doing a computation in a multi-way Turing machine? So in other words, instead of getting one answer here, you're getting this whole collection of answers. How do you think about that? Now, what's this relevant to? The place where it's relevant is chemistry, for example. In chemistry, we're used to doing chemical syntheses where the goal is get one chemical out, go through this whole reaction pathway for the purpose of getting a single chemical out. In computation, we're used to getting one answer out. The question is, what happens when we think about this this computation in okay, so there's this notion that is from yesterday actually of multi-space, which is kind of the multi-way generalization of space. And well, that's not running at all well. But anyway, this is let's see, this is representing kind of the combination of physical space and this branchial space. Anyway, which is to say, Isaac, I completely agree with you that this whole question about distributed computation is super interesting. I think it's going to be hard to wrap our brains around. I think there's going to be one of these things which actually is quite incompatible with the way that human thinking works. I think it's something where our best hope probably is to be able to leverage physics is a very good source of information because both space and quantum mechanics are a story of many things happening in parallel. So but I agree with you. I guess I wouldn't, the concept of, let's use the crowd to build everything. I have to say that in my own experience, there are some things we've managed to define precisely enough that the crowd has helped a lot. But when it comes to sort of building a big sort of story of innovation, I don't think that's a crowd story. I think that's a story. I think the crowd hurts innovation rather than helping it. I think that the existence of people in the crowd is very important, but the crowd as a whole is like, we are now fully institutionalized in doing this. And if it's like, oh, well, actually, there's this new thing to do. No, we're fully institutionalized. We're doing this. We can't do something new. So I think that's it's a complicated thing, and I've spent a lot of my life trying to navigate between sort of what can be best done. How can you set up the best environment for kind of doing innovation and the best setup for being able to deliver innovation to people. And I think it would be wonderful if the magic crowd could do it for one, but I think only in very specific cases can that work. And it's usually when there was already an Encyclopedia Britannica, so you can have a Wikipedia. Without an Encyclopedia Britannica, I think it would have been tough to have a Wikipedia that worked.
Maybe if I can ask a question.
So I neglected to introduce Erez Kaminsky, who is my co-host and co-organizer, and he's going to ask the next question.
Excellent. So Stephen, thank you for joining us, and Isaac as well. One kind of audience question from Saba, and I apologize if I'm not pronouncing the name correctly, is what are your thoughts on models that attempt to predict human behavior and answer trans-scientific questions? Are some things beyond mathematical modeling, regardless of whatever we have the data to create a model? And I'll add to that one more thing. So that's kind of on the humanist economics finance approach. I'll add to that a question looking at the recent publication or upcoming publication of AlphaFold 2, which I think surprised many people, is doing this kind of protein prediction without any physics-based modeling, but purely through data. How do you kind of relate those two things, right? Can you model everything with data? And then does it surprise you that even models with data don't need all these exact rules from physics?
Right. Well, I could try taking this. I mean, I think that in terms of one of the important things from computational irreducibility is the realization that science can't figure everything out. People got the idea, go back 500 years, pre-Copernicus, people were like, common sense is great, I don't need anything like science. Post-Copernicus, people realized, oh, actually, the Earth goes around the sun, that's not intuitively obvious, that's something I have to use science to understand. Roll forward 500 years, and one's at a point where people say, science can solve everything. We just feed in the science and the epidemiology models will tell us exactly what to do, or whatever crazy thing people say. What we realize is computational irreducibility is fascinatingly a thing from within science itself that basically tells you that science has limitations. I mean, it's closely related to Gödel's theorem, things like this. It's all part of this whole story of computation. So first thing to say is there are things where we will not be able to get the exact solution. By the way, we shouldn't be that upset about that, because if we imagine, leading our lives and doing all the things we do, and actually there's this way of just solving to the answer and saying, oh, the answer is 42. Don't bother to lead your life. The answer is going to be 42. That would be a disappointing conclusion about the world. So the fact that there is this sort of computational irreducibility of the passage of time corresponding to something which actually, is irreducible is something in a sense good, but it's also something that limits what science can say. And I think that the first point. So, I mean, the second point is, what's interesting is when you even think of, in terms of irreducibility, a recent thing I've been thinking about is whether value in economics is fundamentally a story of computational irreducibility. Whether this thing that is kind of, where does value come from? Can a cryptocurrency with no underlying economic activity have a genuine value? is that something related to irreducibility? So I think the answer is that there are, at a microscopic level, I'm pretty confident that we can make models of things. Whether we can then say, oh yes, and then the science says this big prediction that's out telling us everything that will happen, that's not going to happen. And people don't yet understand that's not going to happen. And it's an important thing to realize because it has a lot of consequences for people's thinking about what we can expect from the world and what not. I think you had, let's see, there was another part. What was the end of your question? I'm sorry.
Yeah, my other part was just as that relates to when you're thinking of AlphaFold 2 that just published, a big breakthrough prediction. I think a lot of people in the community were surprised that they weren't using any physics-based models, or people assume they're not using any physics.
Yeah, right. So it's the black box versus the how much of the world is just sort of extrapolation, so to speak, or interpolation. How much of the world doesn't need to know how things work? I think that we don't know the answer to that yet. We don't know what the boundaries are yet. I know a former employee of ours named Mohammed Al-Qurashi, who was at Harvard for quite a while. I think he's now at Columbia. Has a more sort of physics-based version of the protein folding thing that finally had works a million times faster than the most recent kind of results there. But I think this question about what aspects of our world are just interpolation, so to speak, and can be done with any old neural net, and what require one to understand more is an interesting question. We don't know the answer to that yet. I have to say, insofar as our brains work quite a lot like neural nets, a lot of the environment in which we choose to live will be an environment in which those kinds of things tend to work. And in other words, there's this complicated feedback loop because, we say, oh, look, all these things work so well. Well, partly we build an environment which is built using things we understand. And the same thing happens with language. Like once you've invented the term table, you invent that because there are lots of table-like things around. Once you invent that term, you start thinking in terms of tables and so on, and then it kind of builds from there. So I suspect that some of the success of some of these neural net things is, yes, when you're relating to things that humans do, because that's pretty close to how aspects of our brains work, it's going to work. I mean, it's interesting that protein folding, to what extent that can be done with protein folding, I don't know. In a lot of these fields, whether there's sort of this continual trade-off between, also, this question of does it encode physics or not? Physics was discovered by humans. Physics, the laws of physics were discovered by a process not unlike this. And whether some particular cluster of neurons in there, so to speak, effectively encodes some physical principle, that's an interesting question. That's a piece of natural science in its own right, to go inside the neural net and figure out what did it figure out. That's a place where, unfortunately, we humans don't have an easy time because the internal language of the neural net was not built for us humans to understand, and we don't. And we have the same problem as understanding any old thing in natural science, going in and trying to see what's going on.
I think there's a tricky bit here, though, that is the word answer and the word understand. Because in many ways, you have many questions for which there is no clear answer by definition. And answer often means an approximation rather than a clear-cut yes or no or a decision. And also, answer may not just be you and nature. Answer may involve various parties who want to prove something to you where you do not have as much capability as those provers. Stephen, you probably know about this recent remarkable result in computer science, which proves that there is a scenario where computational intractability can be solved. Namely, MIP star equals RE, to use the lingo of the field. When you have two provers that can interact with each other, and they are given powers that you as a, they say, polynomial time investigator do not have because you're bounded in your capacity. If these provers have all the ability given beyond limits, and they are entangled by quantum mechanics, it turns out that they can convince you and show you how a Turing machine can halt or will not halt for any program that you might give it. And so this now goes beyond the limits of computational intractability in this very made up artificial scenario. But it's fascinating because a parallel version of the scenario is what is responsible today for things like homomorphic encryption and the ability to do computation on a substrate that you do not trust. And so when thinking about problems, we need to think not just today about answer and question and authority, but rather who are we speaking to and trying to convince of the answer, and to what extent we trust the person who's asking the question. So there's a lot of interesting work about adversarial nature here. And this is also what's going into the novel ingredients, both of the concurrent computing, Byzantine agreement ideas, blockchain, and so forth, because we're no longer talking about me and the computer. We're talking about a whole system. And that's very interesting.
Yeah, right. No, I mean, the thing we're seeing in this sort of analogy between physics and distributed computing, it's all about these causal graphs of what, there's this thing which was, and the whole, I mean, one thing that we see from physics is a large part of the activity of the universe is the knitting together of the consistency of space. And that has its analogies in things like blockchain and so on, of kind of how do you maintain consistency of things, and there's this kind of underlying fabric of computation that's going on. And this is, I mean, I could talk at some length about one of the things that's come out of our physics project is a geometrization of computational complexity theory, which is really interesting and allows you to start thinking about in a general, this thing we call rulal space, which is a kind of the analogy, just as these multi-way systems correspond to different ways to apply the same rule. There's also the notion of rulal space where you're applying all possible rules, and you can start thinking about the geometry of that space. And so then questions like P versus NP become geometric questions in that space, and all kinds of interesting things happen there. And I think it's an interesting question, what the, which I'm not sure we've really thought about quantum computational complexity theory in rulal space. I think we've only gotten as far as classical computational complexity theory in rulal space, and we haven't worked that out completely yet either. But I think this issue of getting answers and so on. I mean, the truth is, this again relates to the whole question of parallel versus non-parallel computation. And I think it's sort of ironic. You talk about procedures where you're doing one step, then the next, then the next. One feature of that is you got to know what happened at one step to go on to the next step, so to speak. And that is indeed very much how us humans seem to want to deal with things. This idea, I mean, again, one thing I've been grappling with recently is this notion, you've got this multi-way Turing machine. It's in this collection of different states. In a sense, it's a quantum system before it got measured. How do you think about that thing which has this whole collection of different states that it's in? And how do you go from there, and how do you make progress? So I'll give you one sort of speculation about that. In molecular computing, which we don't yet for the most part do, but the one example of molecular computation that really works is biology. And one question is it the case that, in doing chemical synthesis, in chemistry and chemical engineering and so on, we're used to the idea of get one product out, synthesize that one product with high yield. But maybe in biology, part of the story is that's not what's happening. It's doing some kind of distributed computation where it isn't getting single answers out, but it's able to make use of some whole collection of answers in a way that we don't yet have a good way to think about. And I agree that it is an important challenge for our language, as every other language actually, but to think about, how do you think about distributed computing? How do you take distributed computing, which I think is pretty alien to us humans, and how do you package it in a way that us humans can reason about it? And as I say, my best hope right now is to use ideas from physics to do that, which I'm really, I don't know how far it's going to get, because I actually think there's going to be limitations. I mean, I know from working, I tried to figure out how to make languages based on graph rewriting back in the 1980s. I could never wrap my brain around it. now finally, from what we've done in physics, I'm a little closer to being able to wrap my brain around that. But I think there are things that are just, for which humans are just not that suitable. I mean, they happen in the universe. Our brains just didn't evolve that way. And that's, you know, that's challenging.
Maybe the key is not to think of us using physics to solve these, but rather societies to fix this. Because in society, many things, people do things independently and simultaneously all the time. And by the way, maybe it's about statistics and statistical thinking as much as it is about simultaneity, because one needs to think about the possibilities of what might happen rather than the single thing that happens. And I'm gaining a lot of hope from the change to today's curricula to K through 12 students, because of the emergence of statistical thinking into the curricula that's now being taught to students going through middle school and high school. So Stephen, it might not be us who understands this, but it might be our kids who may be able to understand this with their better grasp over statistics.
Right. You know, one thing you mentioned society as kind of a model for distributed computing. One of the things I'm interested in right now is in our physics project, and particularly in understanding quantum mechanics. How do we get intuition about quantum mechanics? And so, for example, one of the things that I've been looking at is, you know, when you make a game tree or a game graph, that is another example of basically one of our multi-way systems. And the question is, can we think about, you know, we have some intuition about what happens halfway through a tic-tac-toe game before you know who won and who lost. To what extent can we use the intuition that comes from that to understand what quantum measurement really means? Haven't figured that out completely yet. But so one of the things I've suspected, one of my motivations for making this distributed blockchain that is based on essentially quantum mechanical ideas is one of the very amusing things that may result from that is when people realize that there's an uncertainty principle about bank balances. If you try and measure it too quickly, there's uncertainty in it because of the way that this whole distributed blockchain resolves things. People will get an intuition for what's happening in the physics of it. And so I think these things where, you know, you take them into the everyday world are have the potential to give us much more intuition about how things work, even if all we wanted to do was to understand physics. Now, many more people are interested in understanding, you know, the everyday world than are interested in understanding physics. But yeah, I think that, I mean, I don't know. The thing I was just thinking about recently, as I say, was about economics and about trying to understand sort of the true origin of value in economics and the extent to which that is, you know, I have always had the point of view that that's all about actual economic activity, people making widgets and things. But the question is it really actually about computational irreducibility? Is it really about this sufficiently complex, okay, so in thermodynamics, the phenomenon of entropy increase and heat is basically a story of computational irreducibility. When we say all those motions of molecules got turned into heat, what we mean is they got so jumbled up, so encrypted that we can't realistically untangle them and say this is what was going on. That's a story of computational irreducibility. And the question is, to what extent is sort of value in economics that same kind of thing that heat is in thermodynamics? And so that would be an example. I mean, one of the things that's been missing in social sciences, I mean, people thought in 1800, people thought there was going to be a social physics that was going to be sort of the Newton's laws of social science. That didn't happen.
Psychohistory.
Yes, right. That would be an example of an output from that. But I think that the thing that you know, that happens you know, the thing that I always find striking is, you know, you look at web analytics data from, you know, people using Wolfram Alpha or something, you get all these perfect curves. They're very, very regular, you know, very, you know, smooth curves and so on. It's like that was made by a bunch of humans typing at keyboards. And it looks more precise than what I see from your average particle physics experiment. There should be a theory of this. We don't know what it is. And you know, I think that that's a super interesting thing that you know, we lack some of the formalism, and I think a lot of it has to do with understanding distributed computing better, distributed computation better, and I think that's yes, it is it's something that I've gotten really interested in. As I say, the challenge for a language designer is how do I take those ideas and turn them into something that we humans, whether it's our generation or whether it's 2 generations hence, can actually think in terms of. And by the way, this thing about what happens in subsequent generations, the thing I found really interesting in building Wolfram language is when I started building, well, the precursor of it 40 years ago, the Wolfram language itself 34 years ago, there were ideas that I could not use because people didn't understand them. I mean, I sort of could roughly understand them because I'd studied all sorts of things in mathematical logic and so on, but they were not ambiently understood. And it's been really interesting to me to see over the course of 30 years or so that there are ideas, particularly about things like functional programming and so on, which have become ambiently understood. And so you can actually use them. I mean, in a sense, our computational language leverages a big piece of ambient understanding, which is human language. I mean, we are using, all these names of functions and things are all kind of, leveraging the fact that people more or less understand what that's doing because they understand what that word in human language corresponds to. And so this question about what is ambiently understood, we're gradually building. And in fact, the whole value, I think, of computational language and teaching computational thinking and so on is you get to build in these layers. What is understood today will let one do more that will allow more to be understood in the future. And I think that's a responsibility for teaching the next, the next generation of MIT students and so on, so they can actually, build those successive layers.
So I want to finish this off by collecting a question from the participants. And a few people have asked, can you tell us how to differentiate scientific thinking from computational thinking, or scientific learning from via learning through computation? So unfortunately,
I could try that, or I can try. I mean, I have views about that. I think, the scientific, what is the computational method? What is the scientific method? The scientific method we're often taught is, this thing about observe nature, induce things, get sort of inductive learning from experiments we do in nature. What is the analogous thing? I would say that computational thinking is really a very different story. The computational method is a very different story. It's something much closer to mathematical thinking than it is to scientific thinking. It's something where we're taking kind of ideas about anything and trying to crystallize them into a form that is that can be represented computationally. I mean, the subject matter of scientific thinking is can overlap with the subject matter of computational thinking, but I tend to think that the traditional scientific method is this sort of experiment, observation, model kind of loop. And that's really, you can apply that loop to the computational universe. I've spent a bunch of effort doing that, but that's not the essence of the computational method. The essence of the computational method is to have this kind of language for thinking about things, which is based on computational ideas rather than based on other kinds of things. And in the scientific method, you're not really talking about what kind of a raw material are you using to describe the world. You're talking mostly about the methodology that you use to think about things. At least that would be my, maybe Ike has a crisper version of this.
I think that was very well said. Maybe to crystallize a little bit further, one of the most important pieces of the scientific method is the hypothesis. It's the kind of gestalt that you want to say, oh, it must be this, and you guess at something. Traditionally, in computers, exactly as Stephen has just pointed out, we just don't do this, traditionally. But now, with the emergence of this new model of neural network computation, or renewed model, computers might be doing a little more of that. And so maybe there will be some kind of convergence. But frankly, in science, one of the most important aspects that's not really so taught is that there is often a leap of faith, like there's a conceptualization that came out of nowhere. And I don't see computers doing that yet. I don't see computers growing things from zero training.
I think you're talking about what computers are doing. I think the interesting question in some sense about the computational method is, what does that mean the humans are doing? Computers are merely their tool, just as the experimental lab notebook is merely a tool for the scientific method. I mean, the question is, what is the core of the actual process, the sort of logical process of thinking, the rational process of thinking. And I think a lot of the scientific method is just see what the world does and figure it out from that. Now, by the way, in studying the computational universe, I, for example, have managed to get a huge amount of mileage from doing that same kind of thing, of exploring the computational universe using the scientific method, but using computer experiments rather than physical experiments, and being able to say, okay, we've seen all these different systems, now let's make a general principle from them. It's like seeing all these creatures and deciding we can think about the theory of evolution and so on. That's a scientific method application to the computational universe. But I think the essence of the computational method in itself is a way of talking about how we think about things. For example, mathematical method is we're going to take what we see and we're going to, well, mostly in the mathematical method, when you're doing pure mathematics, it's about theorems and proofs. And that's a methodology. That's a mathematical method. It's about, we come up with these axioms. They are what we assume, then we make these proofs. Now that's, and that has a certain way of structuring itself. The computational method is about, can we express the things we're thinking about in computational terms, and then in kind of a collaboration between us and the computer, understand the consequences of those things. I think that's sort of the key idea. And I think that the notion of can we invent a hypothesis, that's scientific method type stuff. You can absolutely do that in the computational world, but that's a thing we got from the scientific method. The new thing in the computational method is this notion of organizing one's thoughts in computational terms. And that's the thing that is really, that's the new thing. That's the thing we didn't have. I mean, I think, that's the thing, this idea that, and by the way, to comment on your recipes comment, the difference between what we now do with computational thinking and what we have done with recipes is the recipe does not make itself, so to speak. Once you do those steps, and it's like, you do this, you do that, you do that. It's kind of like each step you can foresee what it's going to do. And it is, this. The thing which is really interesting and important and was not anticipated about computation is you press these buttons and then these amazing collection of things happen that you did not expect. I mean, in the recipe setup, it better be the case that the things that happen should be the case, I think, unless you're doing kind of computational cooking where you're enumerating all possible, ways to make some particular thing and doing some sort of computational discovery of cooking forms. But I think that's to me that's the thing which is unique about what we have seen in the last few decades, is this idea that if we crispen up our thinking and are able to cast it in computational terms, then we're on this giant kind of, we just sort of attached ourselves to this sort of giant rocket that allows us lets us go to places that we haven't been able to go before. I mean, I think that's that to me is and this question about, I mean, I think it's very interesting to think about to what extent can the scientific method be done by pure computation? That is, can we form hypotheses? Can we do these kinds of things? I think that that is a story of, okay, so let me give you an analogy to that, which I think is perhaps of use. So about 21 years ago, I found the simplest axiom system for Boolean algebra. Okay, just one of those things. I look for these simple bases for computation. So there's a little tiny axiom, 6 nans equals something. It's from that you can prove all true theorems of Boolean algebra. Okay, the proof of that axiom is correct, I generated by automated theorem proving. It's 100 lemmas long. I printed it in 4-point type on 2 pages. And in 21 years, nobody has understood that proof. And that proof is a deeply non-human proof. That is, it does not contain kind of human style waypoints that allow people to understand it. So this question about what is, when you talk about understanding and what does that correspond to, it's a can we take this thing which we know to be true, we've got a proof, And can we turn that into something which is actually a useful narrative for humans? I mean, I think a lot of what people do when they talk about understanding, scientific understanding of things, they want to tell some kind of story. They want to have some narrative they can tell. Same when they give a good proof. They want to be able to tell some narrative about what's going on. And the question is, can you do that? And when you have your average neural net found this great regularity in protein folding or whatever, what was it doing? Can we tell a story about what it was doing? Can we turn that into something which is like the kind of stories we tend to tell in science? Or is it something which is a deeply non-human kind of way of understanding what's going on? And I think that's that's an interesting matter of natural science. In other words, if you look at what the neural nets do, are there 5 principles of neural net operation that we could give names to, that we humans could learn, that you could be teaching in a class and say, these are the 5 things that are really going on, just as, these are the 5 things that are really going on in atmospheric chemistry or something like that. And that would be a way to sort of understand from natural science what's happening. But I think otherwise this is also a very interesting trade-off, because as we build things computationally, we have a choice between systems that we understand and systems that do as much as they can do. And that's going to be a coming sort of story of kind of ethics and so on, is to what extent do we use systems that are, getting full advantage of computation versus to what extent do we want to be able to tell a human narrative of what's going on.
It's not just a human narrative, if I may just highlight one thing, it's really transferability of knowledge so that you can come up with a narrative which generates more narratives. And if I may put it in a Wolfram-like way, it might be, I'd like a Mathematica program which generates Mathematica programs so that Mathematica can talk to Mathematica and convince Mathematica of the correctness of Mathematica.
Well, so right, but so what you're describing there, you are explaining what, since I've spent a large part of my life as a computational language designer, I have to think about, what you're asking for is essentially elements of computational language that describe what's going on. You're asking, and in fact, what I see my role in doing computational language design, there's this infinite space of possible computations out there, which are the little nuggets of computation that are important enough and understandable enough that we should give them names and that people can then string them together to think about things. And that's, I think that is what you say is, is very much correct, that's the core thing, is to find those elements of sort of, the elements of computation that do 2 things. They're both readily useful in doing computation and they connect to things that we humans understand. Because it doesn't do us, in creating sort of functionality for Wolfram language, one of the issues is always, yes, there's this thing, and you can, it may be even a fairly small piece of code, should we give it a name? If the name we give it helps you understand what it is based on your ambient understanding of the world, then it's worth giving it a name. If the name is so obscure that you might as well just see that idiom and not try and give it a separate name, then just let it be that idiom. But again, this is the thing where, there's this complicated feedback loop between the things that we discover and we give names to and we put in languages and so on, are the things that we then build on top of. And then we kind of often get very confused. People say, oh, look how fantastically successful mathematics is in physics. Well, that's because we built our physics to be the things that we could work in terms of using the mathematics that we have. And I think that's, so there's this sort of gradual process of making use of things that we, have an encapsulation of and being able to build from that.
And I think maybe this is a good point to kind of summarize the session and just say that all these questions, right? Like, what are the models? How do you think about models? What is computational thinking exactly? We're going to discuss throughout this class, starting kind of with the Wednesday session about computational economics and finance, as well as the sessions next week about the physical sciences, which will include Dr. Hamd El-Qureshi, which Stephen mentioned earlier, who will come here and give a talk next Wednesday about these things exactly. So I think I speak on behalf of myself and Dr. Carter and all the attendees that we really can't thank both Dr. Stephen Wolfram and Dr. Isaac Chang enough for coming here and giving us some of their time and insight. And we're very excited to kind of see how this whole course rolls forward. I don't know if Craig perhaps has something to share as well.
No, just my profound thanks. And I could listen to this for hours, but unfortunately we have to go. But I've enjoyed this very much.
I'm so disappointed because I'm scrolling through the questions here and there's some really great questions here.
There
Wow.
are great questions. Yeah.
Okay, I'm disappointed we don't get to talk about some of these another time, perhaps.
Yeah. Thank you very much. I'm going to end it here. Profound thanks, and let's wish everybody a better 2021.
Sounds
Pleasure.
good. All right.
Bye-bye.
See you. Bye.